So my name is Thomas. I'm the CEO of TensorTech. So today we will be introducing this topic, the control moment gyroscope for small satellites. So let me briefly introduce the agenda today. So first of all, I will make a brief introduction for you about TensorTech and what we do. And secondly, we will introduce the moment when people should go to use CMG. And besides that, we will also propose some solutions to solve the existing issues of using CMG. And lastly, we will also introduce to you about a ADCS that is based on the CMG technology. And so I think that today we didn't have too much people today, so if you have any question, welcome, just raise your hand and I can answer some questions for you. Okay. So let's get started. Yeah. So a little bit about TensorTech, that we provide motion control solutions for satellites. And we were founded in 2019, and our headquarters is based in Taiwan. So majorly we manufacture and also design the components and also subsystems for the ADCS. And we have two offices, one in Taiwan and one in the USA. So right now we are currently serving some commercial satellite players around the world, and of course also some government players in Asia, also in the USA. Besides that, we also provide some solutions for academic players like the universities or like some research institutes. And here are the four major product lines that is offered by TensorTech. We do components for the ADCS, including things like a torque rod, like the control moment gyroscope itself, and also some attitude sensors, like fine sun sensors. And we also do the entire ADCS systems, so that are included with software and also the hardware. So the software side includes some estimating that will gather data from our sensors and do some filtering and do some calibration of its own satellites or parameters. And also it will control the satellite's orientation with some embedded automatic modes. And besides that, we also do the ADCS testbed. So it is a kind of equipment that for TensorTech or for our clients, we can test the ADCS on ground. So these testbeds include some spherical air bearing and also compass cage and also some solar simulator, so that we can test and verify some control algorithms or also the behavior of our CMG on the ground. And lastly, we also do some service, including the testing service using our ADCS testbed. Or we also do some solutions that is dedicated to some customization software solutions to help people to build some autonomous attitude control modes for them to easily use our system in space. Okay. So let's get into our topic today, about this CMG, control moment gyroscope. So first, to begin, I'd like to mention that there are actually several types of angular momentum exchanging devices for spacecraft, and the most commonly used is something we call reaction wheel. And usually people need at least 3 reaction wheels, or sometimes people use 4 reaction wheels for redundancy and to eliminate some issues occurs when building is never possible. Yeah. So, so this principle, the principle between reaction wheel and CMG are actually similar. They all exchange angular momentum with the spacecraft itself. But we do find that there are some pros and cons for the traditional reaction wheel technology. So the benefits include that those CMGs are usually simpler in terms of their system dynamics. So it's easier to build an ADCS based on this reaction wheel technology. Thank you. And also reaction wheels, they are smaller in size when when the angular momentum storage capability are the same, usually these reaction wheels, they are smaller. So that means their angular momentum to volume density is higher, or their angular momentum to mass density is higher compared to conventional gyroscope. But also there are some disadvantage of reaction wheel that is majorly related to its power consumption, especially when people are building some agile satellites, when they need to maneuver in a faster speed or estimate the satellite in a larger torque. So there are some missions started to adopting these. The next topic that I'm going to cover is the Single-Gimbal CMG. And before we jump into that, we can firstly make a dimensional analysis about the size and also the power of the spacecraft. And so it can better facilitate us to know when would be a better timing for us to adopt CMG technology. So actually this result can be also defined by a conference paper in the SmallSat conference in 2012, I suppose. Yeah, so this interesting dimensional analysis states that if we assume the size of a satellite to be a cube and with a dimension of d, then the volume of this satellite would be proportional to d to the power of 3, and then the moment of inertia would be proportional to d to the power of 5. However, the power budget of the satellite is usually proportional to the surface area. These are the only areas that people can install solar panel. So the power budget itself is proportional to d to the power of 2. So that means when the satellite getting larger, that means the d gets larger. Then usually the ratio between the available power budget to the moment of inertia will become large. So that means when satellite getting larger, people need something have a larger torque to power ratio. So that's a dimension, the result of this dimensional analysis. So it tells us that when your satellite getting larger, you need something have a larger torque to power ratio. But to be how large is something we call a large satellite, or to how small is something we call a small satellite. That's something to be discussed. So in the later on section, I will try to elaborate these ideas. Yeah. So that's why people started to adopt these Single-Gimbal CMG when they found their satellite is large enough to scale that they need this kind of components with larger torque to power ratio. So as you can see that each Single-Gimbal CMG, they still have a spinning disc inside. So that's something, for example, for this CMG, there's still a disc inside spinning, just like a traditional reaction wheel. But besides that spinning disc, there are also a gimbal motor beneath the spinning disc, so that you have totally 2 degrees of freedom for CMG. And so here are 3 examples of available CMGs on the market, including the one made by Dual-Gimbal, the one made by Blue Canyon, the one made by Airbus. And you can see that those 3 companies, they have products in different range of angular momentum. So that, for example, like Airbus products, they cover a wider range of available products, and like Blue Canyon and Dual-Gimbal, they both target a different range of the angular momentum storage capability. But 3 CMGs, they all have a similar advantage, that is, they have a larger torque to power ratio compared to the traditional reaction wheel. And that's usually their selling point to convince users to use this kind of technology. But there also comes with some disadvantage, is that these CMG are usually complicated in its steering law. So for the user to adopt this technology, they need to develop dedicated software to deal with this steering law, to avoid circularity, and also to to design the cluster with a suitable angular momentum envelope. And also, those traditional single-gimbal CMG, they are usually larger in size compared to reaction wheel. That is, they have less angular momentum to volume ratio, or they have less angular momentum to mass ratio. And besides that, usually these CMG, they have a slip ring on the inner motor, because the inner motor, they need also some electrical connectors to input with those control signal and also the driving power of the inner motor of these CMGs. So they need a slip ring to conduct those electric currents inside to the spinning motor of the CMG. So these slip rings are usually limited to the lifetime of the CMG. And so usually, for example, some single-gimbal CMG suppliers, they will provide some specification for the clients that how many gimbal maneuver is tested for this kind of CMG. And usually it's limited, so that some steering wheel or some ADCS software, they will have to deal with this situation by reducing the number of gimbal maneuver so that they can maximize the lifetime of this CMG. Yeah. So these are some existing disadvantages of the CMG. And then next, we also introduce you about how and also when this torque-to-power ratio becomes more significant before we jump into another type of single-gimbal CMG that is run by Spherical. Okay, so I will start to talk with some mathematics now. And so these are the two system dynamics of reaction wheel and also single-gimbal CMG. So this system dynamics exists in a condition when the spin rate of the satellite is 0. So for traditional reaction wheels, you obtain torque when you are accelerating your rotor. So that is how you get tau z here. This is the torque in z direction, and you obtain it by accelerating the spin of this guy. And also, this is the principle of single-gimbal CMG. That let's see this coordinate frame here. They are it is attached in the gimbal reference frame. So actually, you have majorly there are two torques that you can utilize. The first one is the torque in GS direction. So these are something also similar in principle to the reaction wheel, that you obtain torque in the GS direction by accelerating or deaccelerating the rotor in the GS direction. So you get a tau s here in the GS direction. And then you will get another torque in the GT direction. That's something we call the gyroscopic torque, or something we call gyro moment. So when there is an angular momentum storage in the GS direction, and you apply an angular velocity in the GG direction, then people will get a torque in the GT direction. So this is, you can see the torque in the T direction here. That is proportional to the angular momentum stored in the GS direction, and also it is also proportional to the angular velocity in the GG direction. Yeah. And usually when you are accelerating or deaccelerating the gimbal axis in the GG direction, you will also get a torque. Usually when we are designing our ADCS software, we will treat it as a disturbance. That is a torque that we didn't want. And usually they are smaller in scale compared to the gyroscopic torque or these reaction wheel torque in the tau s direction. Okay. And here's one interesting thing that people can observe is that for traditional reaction wheel, the direction of the angular velocity and also the direction of the torque, they are basically parallel to each other. And for single-gimbal CMG, the direction of the gyroscopic torque and the direction of the angular momentum, angular velocity, they are basically nearly orthogonal to each other. So this gives us some good characteristic here, because we know that the mechanical power is the dot product of the vector of torque and the vector of angular velocity. So that for a reaction wheel, that there's no chance for you to eliminate the mechanical power. But for a single-gimbal CMG, when you are majorly exerting the gyroscopic torque, there is a chance for you to eliminate the mechanical power. Okay. So allow me to get in more details about the system dynamics and also the power analysis here. So, so then we can start to make some calculation about the power consumption of reaction wheel and also the single-gimbal CMG. So first of all, that those components, they are basically motors. So for motors, there are certain power consumptions like the iron loss here, like this term, iron loss, and also copper loss. So by what we mean copper loss here is that when we are applying electrical currents to our copper coils, and they usually induce some loss because through heat. And also we have a mechanical power here. So by summing these three terms up, we get the total power consumption of our angular momentum exchanging device. So of course this is not calculating the other power consumption for the rest of the subsystems in our satellites. We are only calculating the power consumption of our angular momentum exchanging devices. So we can further break down the composition of our mechanical power. So we can see that for the mechanical power, they are the power that is required to overcome the friction. And also they are power required for the rotor to maneuver itself. And also they are power required for the satellite to maneuver itself. And so we can get into more details by looking into this term, P maneuver, that is essentially the sum of the rotor to maneuver and also the sum for the satellite to maneuver itself. So we might have multiple angular momentum exchanging devices for satellites. For example, people might use 4 reaction wheels, or people might use 4 CMG or even 6 CMG per satellite. So there is a sum here. So you have to sum up the torque induced by each angular momentum exchanging device and also the angular rate of its rotor respect to the inertial frame. Okay, and so we can so we need to notice that this angular velocity here is actually the rotor frame referencing to the inertial frame. So we can further break down it into 2 terms here. One is the angular velocity referencing the rotor frame to the satellite frame, and the other is the term referencing the satellite frame to the inertial frame. Okay, so then this gives us some results here that we can break down this mechanical power term into 2 by C. We can try to ignore the process here. But anyway, the result looks like this. So you get one term that is the dot product of the tau total. That means the total torque that these angular momentum exchanging devices array that apply to the satellites. And it needs to be dot product with the angular velocity of the satellite itself. So actually this term is what we call the power required for the satellite to maneuver itself. So for example, when we are accelerating the satellite by applying torque, then we obviously will consume some power. And there are still another term here that is that exists when the torque exerted by each angular momentum exchanging device dot product with the angular velocity referencing the rotor frame and satellite frame. So one can notice that if people are using reaction wheel here, then we have this term. But when people are using the control moment gyroscope, then this term vanished. So it is because that for when using CMGs, we are majorly exerting the gyroscopic torque. So the vector here, tau n, and also the omega, referencing the rotor frame to satellite frame, these 2 vectors, they are basically orthogonal to each other. So that when using CMG, this term vanishes. But when using the reaction wheel, this term exists. And so by calculating this term, we can compare the difference between the power consumption of CMG and reaction wheel. And so in the later on pages, I will show you some results of this calculation. And so this is the difference in mechanical power. And so here we can also make an assumption that for the CMG and also for reaction wheel, their iron loss and copper loss, that should be similar, or there should be not a big difference between each other. So we can say that the major power consumption difference between CMG and reaction wheel occur by this term. Does anyone have any questions so far? So here is some calculation results by assuming a certain maneuver trajectory of the satellite. So this maneuver trajectory is actually suggested by a conference paper here. That if you are interested, that we will be sharing this presentation slide after this side meeting. And if you are interested, you can try to look it up. But this is a maneuver trajectory that is suggested by a skybox imaging. So what we do here is that it assumes that an Earth observation satellite, when it's passing by its target, it is doing maneuver by making the setup here to be firstly in the negative region and go to a positive region and swing back and forth to do a sinusoidal repetition here. And so during this process, we observe that obviously there are certain times that you are trying to accelerate the satellites by applying torque. So that's when you consume some mechanical power. And also when you reaches to this flat region here, then you majorly maintain the angular velocity of your angular momentum showing devices by letting the satellite keep steering by maintaining its angular velocity. And then you need to apply a negative torque so that you can get the rotational angle of the spacecraft back to the negative region. So this is how you complete the cycle and how the angular velocity of the satellite looks like, and also the acceleration curve of your satellite looks like. If you are trying to make your satellite to maneuver back and forth, and do this rotation for capturing more images per pass. So that is the plan. This is how this profile looks like. So then we can make some assumption here, like for us to calculate the differences between the power consumption of reaction wheel and the power consumption of control and gyroscope. So first, we assume that the moment of inertia of the reaction wheel is in this ratio of the total moment of inertia of the satellite. And also the satellite is in a shape of a tube, like we suggested in the previous slides. And also it's in a 550 kilometer SSO orbit. And also we also make some other assumption here. And so we can see this is a result. This is the additional power consumption for the reaction wheel compared to control and gyroscope. And versus to the total satellite power budget. So the total satellite power budget is calculated by the previous slide. Then we assume that the satellite has only solar panel in its surface. So it's a body fixed solar panel, but without deployable solar panel. So this is how we calculate its power budget. And also this is the additional power budget for a reaction wheel that is suggested by the term in the previous page. That is basically the calculation result of this term. Okay? So we can see that when the satellite gets larger, that means its moment of inertia gets larger. And we will get a larger power consumption of the reaction wheel in comparing to the traditional true to CMGs. So this is the calculation result here is a percentage to the satellite power budget. So you can see that up to this line here of 40%, that's basically maximum acceptable power consumption of these ADCS. Yeah, so, and also another axis here is the skew angle of the satellite. Yeah, so we define a skew angle from 12 degree to up to 60 degree. And the reason why that the skew angle, when it gets larger, then we have a lower power consumption is because when the skew angle gets larger, then we will have a longer period of time staying in this flat region here. So that is why the average power consumption of the satellite maneuver when the skew angle is larger, then we will consume less power. Okay. So does anyone have questions here for this the result of this slide? So as the previous piece suggested, that when the satellite gets larger, that usually people will need this kind of angular momentum exchange device with larger torque-to-power ratio. So here are some classic examples of spacecraft using CMG. So for example, there are Maxar's worldview series satellite, and I noticed there are one client from Maxar today. Yeah, and so this is a very classic example of a spacecraft using CMG. And this is actually a Earth observation satellite that is trying to increase the images that one satellite can get per pass, so that it needs a larger zoom rate, so that it can capture more images. So these Maxar's satellites that use Single-Gimbal CMG, and so this is something we call the HL satellite. Of course, the definition of HL satellite is not strictly defined. That some people think over 1 degree per second is something we call HL, and some people think over 3 degrees per second is something we call HL. But anyway, that's for this kind of EO satellite, you need larger zoom rate. And another example is spacecraft that has very large moment of inertia, like our International Space Station. So one small difference between the CMG of the International Space Station and the Maxar's worldview series satellite is that the CMG for ISS is something we call Dual-Gimbal CMG, but the CMG on the worldview satellite is something we call the Single-Gimbal CMG. So those types of CMG, they have its own pros and cons, and I will be elaborating these details in the later sections. In order to solve the existing problem of the traditional CMG and then how this technology looks like. So, as mentioned earlier in the previous section, the traditional Single-Gimbal CMG, they have actually 2 motors. So one motor for the inner rotor, that's the spinning disc. Another motor for gimbal, so that's something we call gimbal motor. But this additional motor makes the angular momentum to mass ratio of the traditional Single-Gimbal CMG to be worse than the traditional reaction wheels. So we are developing a technology that is based on this Spherical motor. So later on, we'll try to activate this model on the table to demonstrate how these Single-Gimbal CMG drive by Spherical motor works. Okay, so this is how our Single-Gimbal CMG looks like. So inside there are still 1 gimbal, as the traditional Single-Gimbal CMG has. And inside the gimbal, there is a rotor spinning. So that's the same compared to a traditional Single-Gimbal CMG. But what's different is that in this gimbal, there is no motor for spinning up the rotor of this CMG. So instead, on this Spherical rotor, there are magnets, permanent magnets on top of it. So later on, if you are interested, you can come by and see how this rotor looks like. So inside, this rotor can spin in these degrees of freedom, but without a inner rotor motor to spin up this disk. But this disk is right by the coils external to the gimbal. So these are the coils here that are installed outside of the gimbal here. Okay. So this gives us some advantage to eliminate the slip ring, because traditionally the CMGs requires one slip rings for you to apply electrical currents to the motor inside the gimbal. Yeah, but for this spherical motor design, the slip ring can be removed so that we can have a much higher gimbal maneuver lifetime compared to the traditional CMGs. So there's basically no lifetime retention due to the slip ring. Okay. And secondly, because there's no additional gimbal motor, so this Single-Gimbal CMG can be much smaller. It's basically the size of a sphere that is surrounded to this inner rotor. But
is it common, or is it maybe necessary that the gimbal has unlimited throw?
You mean the gimbal?
The vertical axis there, that's the gimbal axis.
Yes.
Does that have to be able to go forever? It seems like plus or minus 180 would be enough.
Oh yeah, that's right. So some traditional designs, they use an electrical cable to conduct electrical currents into the gimbal. But then there will be some limitations there in the steering rod. Then the steering rod needs to take care of this, so to prevent those cables to twist it by itself. Yeah, and then we'll give some limitation to the control. Yeah, so
you don't have any electrical interface going across the gimbal axis.
Yeah, for our design, because this is a spherical motor, so there is no cable necessary or a slip ring required to conduct electrical current inside the rotor. Okay, and then but there are also some disadvantage of this Single-Gimbal CMG drive by spherical motor is that this design is now a inner rotor design, but mostly some reaction wheels, they are usually outer rotor design, so that gives these reaction wheel larger angular momentum or a larger moment of inertia. So this is a disadvantage of this spherical motor technology. But of course, there is a possibility for us to make the rotor to be external to the coil. So basically, like there's a company called Honeywell that is developing this kind of technology. They build these reaction sphere with an external rotor, but they will sacrifice something. That means the traveling angle of those rotors will be limited, because when you put the rotor outside of the coils, then there are certain angles that you cannot rotate to, because you still need somewhere to install the coils of the spherical motor. So that's why we make this in the rotor design, so the rotation angle will not be limited. But we'll see how this technology will evolve by time.
I can see that you get rid of the slip ring, but now the coils of that inner rotor rotates with the gimbal. So from a balancing point of view, if you have a high stability mission, you can easily balance the internal rotor to fine precision. But now to balance the rotating rotor with the coils, I think that will be a more difficult problem. I know the rotation rate is much smaller than the inner rotor, but still you need to balance it.
The coils are in the base, not on the...
The coil is not rotating. So here is a inner view of how the mechanical structure looks like. So so the moving part is this gimbal and also the rotor inside. And also the parts that stationary is stationary compared to the spacecraft is those coils.
The coils are stationary, they don't rotate with the gimbal.
Yes, okay. The coils are stationary. Yeah. So this is how its inner structure looks like. So this is the mechanical parts and also the gimbal part. So usually what we need to do is also a dynamic imbalance. We need to also do the calibration of its rotor rotors in balance, like the traditional CMG has to do. But since these gimballing axes usually rotate in a slower speed, so we didn't calibrate these gimballing axes to that fine grade compared to inner rotor axis. Since the inner rotor axis usually spin up to from 6,000 RPM up to 8,000, and actually the limitation of design goes up to 12,000 RPM. And so in TensorTech, we also do extensive work on doing this magnetic field design by dealing with how the magnetic field inside the rotor interacts with these coils. And of course, for the larger CMGs of drive by these spherical motors, the number of coils and also the number of magnets inside the rotor also gets a larger number as well. Okay, so,
Excuse me.
Yeah.
I have to run to another meeting, but will you be available for questions at your booth?
yeah, sure. Please come by our booth at 170 in the field house.
Okay. Thank you.
So here is a video demonstrating how these CMG drive-by spherical motor works. I'm afraid the internet is a little bit stuck. So now what this CMG is doing is that it is installed on top of a spherical air bearing. So as the video you can see on the right hand side, that this spherical air bearing can help us to create a nearly frictionless environment for us to test our CMG on ground. Actually, this spherical air bearing is also part of TensorTech's ADCS testbed for us to developing our ADCS or also our CMG. So what this CMG now is doing is that it is exerting gyroscopic torque in the XY plane. Actually, it is saturated in one axis and desaturated in one axis and saturated in another axis. So it is actually not a usual operation of a CMG in space, but this is a interesting demo for you to see that how it actually works. So actually we have other videos of these CMGs in TensorTech's YouTube channel. So if you are interested, you can also check it out on our YouTube channel. So now this equipment is probing the electrical currents inside the CMG. So what CMG do is that it maintains the constant inner rotor speed, but the tilting angle goes from the 0 degree to the to 360 and go back to 0 and go back to 360. And it is an open loop control now. It doesn't do a closed loop by referencing back the measurement results of the other inertia sensor. So it is purely exerting the gyroscopic torque right now. Okay, so let's go into the next section. How do we use the CMG? And also, as previously suggested, that one obstacles for people to adopt CMG is that they are typically more difficult to control. It's because of its steering mode is more complicated. So that's why actually for TensorTech, in the very beginning of TensorTech, back in 4 or 5 years ago, we originally just want to be a CMG company, and we just want to sell the CMG. But then we found that it's hard for people to adopt and also to develop their own control algorithm based on CMG, since usually the ADCS engineer are more familiar with traditional reaction groups. So then we started to develop our own ADCS based on CMG, so that people can adapt our CMG with without the need to implement their own algorithm. But we help them to wrap up these algorithms together. So here are some examples, and also how we try to eliminate the difficulty for our clients to adopt the CMG. So as you can see now, this CMG is actually in the core of this ADCS. So this is a standard product developed by Tensor Tech, and this ADCS is designed for a 6U chipset. So this single-gimbal CMG can fit into the bottom in a two-mark camera. So it's basically outside of the spacecraft. So inside of the spacecraft, it occupies a 0.25U inside chipset. And on top of this CMG, there are also other additive sensors like fine-sun sensor and also magnetic materials, and also some other optional components there. So for this design, only one single-gimbal CMG is used. So as you can see, that's the one single-gimbal CMG, especially when its inner rotor axis has a variable speed function, so you get 2 axes of control. So for this model here, the third axis is actually controlled by a torque. And besides the one single CMG's configuration, we also have other configuration like adjacent pair or a more classic pyramid cluster of CMG. So this is something more frequently seen in large spacecraft or in a space station. People usually use for CMGs to form a pyramid cluster. And there are some skew angle need to be designed so we can optimize the angular momentum envelope for the specific mission and also the satellite's normal mission. Yeah, so like these are 2 instances of CMG clusters. Like the one you see here, ADCS 20M. This is something we call adjacent pair. That means for this pyramid cluster here, what adjacent pair means is that only one CMG1 and also CMG3 is installed, and the CMG2 and CMG4 is removed. That's something we call adjacent pair. And also there are something we call opposite pair. That is, you have CMG1 and CMG2, but usually opposite pair is not preferred in a cluster design because its angular momentum envelope will get more flat unless your mission has a specific needs or your satellite design is more unique. Otherwise, mostly people use adjacent pair or pyramid cluster. So there are different characteristics when adopting adjacent pair or pyramid cluster. Besides, for adjacent pair, in order to get 3 axes of the control for the satellites, that it doesn't have redundancy by itself. So when one CMG fails, the adjacent pair can only control 2 axes of the satellite, and the 3rd axis of the satellite is to be controlled by torque. But for the pyramid cluster, that it can tolerate up to 2 failures of the CMGs. So this is why larger spacecraft they usually prefer this kind of pyramid cluster design. So here is a ADCS 40M that is designed for 16U chipsets using this kind of pyramid cluster. But we also get a larger version of the ADCS that uses a CMG up to 1 Newton meter second. So this is how these ADCS looks like. For this case, it is an adjacent pair CMG. So the main control board of our ADCS is used to drive 2 CMGs. And actually there are also some people that they already have the capability of developing the ADCS, but all they need is a actuator control board for the CMGs. So this is also how this ADCS MCB can function. It can just function as a electronic board for the user to synchronize and to execute the steering law of the CMG, so that they can just treat this CMG as a torque output unit, but we deal with the steering law inside these electronic boxes. And also the same with these ADCS 40M. that the ADCS consists with 4 CMGs, and also these ADCS MCB can function as a ADCS computer, or it can also function as a actuator control board for helping the user to synchronize and also do the steering of the CMGs. Yeah, and inside these ADCS, there are already some embedded control modes, like traditional ADCS modules that you might see on the market, that include some pointing, tracking, LUH controlling modes. So actually the goal here is to helping our customers to be able to enjoy the benefit brought by the CMG, but to reduce the efforts they require to integrate this kind of system. So that's why now TensorTech is majorly providing ADCS over the components. And of course, there are still some component users so far, but now the majority of the products that we bring to the market is the ADCS itself. Okay, so lastly, I would like to introduce you to the ultimate goal of TensorTech CMG technology roadmap, and also what's upcoming next for our technology. So, as introduced earlier, that there are so-called Single-Gimbal CMG, both driven by 2 traditional motors or driving by 1 Spherical motor. But actually, there are another types of CMG that is called Dual-Gimbal CMG. So these Dual-Gimbal CMG were actually adopted by space stations. So what's the difference between these Dual-Gimbal CMG? So they have 2 gimbals here. For example, you can see that here is the outer gimbal here, and also an inner gimbal. That's the black object you see in the picture. So for traditional Single-Gimbal CMG, there's only a spin axis and also an inner gimbal. But what Dual-Gimbal CMG does is that it adds another outer gimbal outside of the inner gimbal, so that it gives the CMG 3 degrees of freedom. And also, there are more slip ring here, and also there are some limitations like gimbal lock for this Dual-Gimbal CMG. So as you can see that this gimbal lock problem is frequently seen in textbooks, and so there are already various ways for people to adjust and also to deal with this gimbal lock issue, but still there is a limitation that comes from mechanical design itself. And what are the benefits of these Dual-Gimbal CMG? That people usually can use it as a mechanical battery, and also since they have 3 degrees of freedom, in principle they can just use 1 Dual-Gimbal CMG to control the 3 axes of the satellite. But however, there is one axis, the one axis of torque that is provided by the spin axis that has less efficient compared to the rest 2 axes of the Dual-Gimbal CMG, because the other two axes is based on the gyroscopic torque, but the inner rotor axis is based on the accelerating or decelerating the inner rotor speed. Okay, so this is the traditional Dual-Gimbal CMG, but what TensorTech up to is something we call Gimballess CMG that I will introduce in the following page. So, what is a Gimballess CMG? So, this is actually a 6 degrees of freedom reaction speed that is both levitated by the magnetic fields. Also, there is a magnetic bearing, and also it can be spin up in 3 axes. So, this is something we are currently developing, and actually the version of CMG you see on the desk, the Single-Gimbal CMG based on the Spherical motor is a stepping stone for us to build this Gimballess CMG. So this Gimballess CMG is something we imagine to be the ultimate shape of the CMG in the future. But before we build this and also to launch it into space and also fully validate it in space, we need something to serve as a stepping stone. That is the Single-Gimbal CMG driven by Spherical motor that you see on the desk. So for this Gimballess CMG, it is also actuated by spherical motor. But what's different is that it can also be furtherly levitated by the magnetic bearing, so that the gimbal lock issue can be eliminated. Because before, in the Dual-Gimbal CMG, there are mechanical bearing in 3 axes. So that means there must be a gimbal lock issue. So you either solve it by software, or that, but when you do it, then there are some limitations for your operation. And also, when the inner rotor is levitated by magnetic field, it gives us a much higher rotational speed for the inner rotor, so that we can store a much higher angular momentum in the constrained volume. So this is how the ultimate shape of CMG that tensor text will. Yeah, and also what it can do is like Dual-Gimbal CMG, it can do 3 axis control by one CMG, but there's still one axis that is less efficient because it's spin up by accelerating or deaccelerating the inner rotor. Okay, so to make a conclusion, that's I think what tensor tech and also CMG technology is up to, and also the meaning of CMG for me is about elegancy. So we are pursuing a way to control or maneuver your satellite in a more elegant way. First is by the CMG technology, and secondly is by using spherical motor instead of multiple traditional motor. So this is what tensor techs pursue. And thank you for attending our seminar today, and I'm welcome to have any questions.
Yes, I'm also a big fan of CMGs, but it has its limitations, as you pointed out. My question is, this Gimballess CMG sounds like an ideal solution, but how are you going to protect it against launch vibrations initially? Because you only levitate this initially, the CMG must be without any power, I assume. So you have to protect it mechanically so that the inner rotor doesn't destroy your CMG when you launch the satellite.
Yeah.
And the other question is magnetically, in your ADCS system, you say there is a magnetometer. But that magnetometer, I assume, is disturbed by your magnetic fields of the CMG. How do you handle that situation? Because you cannot switch off the coils to take a magnetic field measurement. It must be continuously powered to CMG.
Yeah. So the first question is actually very insightful. That is also a problem that we are currently solving. Yeah, because when the satellite is launching, the CMG has to be powered off. So that we have to prevent the rotor keep knocking the stator. Otherwise, the stator will be sabotaged. So now what we develop is to use several solenoids. So several supporting stick there. So it is there are springs there. So when the CMG is powered off, these springs they will support the rotor during launch, and then when it's going into space, then we apply electrical current to those solenoids and let it leave the rotor. Then let the rotor to be supported by a magnetic field. That's the current strategy that we are developing. But I think this might not be the only way. There might be other ways to solve this issue. But that's currently the way that we are trying.
Yeah, I assume it's latched solenoid so that you don't need to power them continuously, because that will also be bad for your power budget.
Yeah, that's right. Yeah.
And the magnetic disturbance issue?
Yeah. So can you repeat the question?
Now, in your ADCS solution with your CMGs, your control board, I assume your magnetometer sits on the control board. So that's very close to the coils of your CMG. So if the coils is controlling the CMG, it will disturb the magnetic field measurement of the magnetometer. How do you prevent that?
Yeah. So for this particular model of the ADCS, so there are 6 5-sun sensors, and also for each 5-sun sensor, there are a magnetometer on board. So a 3-axis magnetometer on each sun sensor. So 5 sun sensors are already installed on the tuner head, which is nearby the CMG. So their readings are less optimal than placing the magnetometer on elsewhere. So the rest, one last 5 sun sensor and also the magnetometer is placed on opposite sides of the satellite, because these 5 sun sensors already capture most of the field of view of the sun, but the rest need to cover the position that is opposite to the tuner head, so that we can get sufficient field of view. Yeah, so we usually use the readings from the one last magnetometer to do the altitude determination.
From the one that's furthest away.
Yeah, that's right. And there is a suggested distance for the user to mount these 5 sun sensor magnetometer.
What is the field of view of the sun sensors?
It is 60 degrees half angle.
And accuracy?
Accuracy
of the sun sensors.
for 0.2 degree, I think it's 3 sigma. Yeah.
So for your CMG, for the gimbal motor that you have, how do you measure the angular changes of your gimbal motor, and how does that translate into the torque resolution that you get out of your CMG?
So for gimbal axis, actually what we have is also a magnetic encoder. So in the gimbal axis. So actually, when you see in the bottom of this gimbal, there is a small magnet on the bottom, and so there are magnetic encoder also on the PCB board beneath these CMG. So we use this magnetic encoder to measure its rotational angle.
What's the resolution of that encoder?
So the resolution of encoder is up to 0.5 degree for this version of the CMG.
And what would be the torque resolution at the end when you actually trying to figure out how accurately we could actually point the satellite if you have to keep pointing inertially?
Yeah, right now the torque accuracy that we measured and validated so far is 1%. Yeah, and they might be limited by our measurement instruments, so there might be room for us to improve it as well. Improving our measurement instruments, also the control and estimation algorithm inside. And now this the test result is 1%.
I think maybe it's beginner's question. I think you said that there's bound to be a control authority asymmetry where you're weaker on the spin axis than on the gimbal axis, right? So if you want 3-axis control, maybe you need 2 CMGs. But at an unfortunate alignment, you'll still be limited by the spin torque mode.
Mm-hmm.
So does that eliminate the benefit? Is there still benefit? Why, if so, why? Why is there still benefit? It seems like I'll get aligned, and maybe, sorry for sort of a 2-part question, but if I'm cruising along, I decide to make a yaw maneuver and torque the CMG down, so there's a momentum increment and the spacecraft starts to turn. Now I have to process that moment. And I might have to do that with the spin axis of the other mode. So is that the limiting factor in what I can squeeze out of the system?
Sure. So let me explain this issue with some previous slides. So actually, in my point of view, that the spin axis doesn't limit the control authority, but it's just less efficient than the gyro moment. So you can see that this is the system dynamics of a single-gimbal CMG. So that the spin axis is this one, GS, and then the gyro moment axis is in GT direction. Yeah, so it is better for the user to exert torque in the GT axis, which has much more efficient than you exert torque in the GS direction. But the limitation of the CMG cluster, especially when you are building an adjacent pair of the CMG, so there are still some directions that you need to exert torque by the spin torque. Yeah, so that makes the efficiency less. In that case, the efficiency will just be similar to the reaction wheel. Yeah, but if you use the pyramid cluster like this is a pyramid cluster, then you can fully exerting gyroscopic torque.
So do you want to say it's as good as quad wheels, but you only need two, excluding the gimbal cost? If the gimbal cost was 0, I would just use two similarly sized.
Yeah. Then if the user wants to reduce cost, then they can just go with these.
I think you've answered my question.
Yeah. Just go with the adjacent pair of the CMG. That means they are.
And does everyone typically operate them in small angles so that you don't have to use much spin torque? Or do you use large angles anyway?
Yeah, for traveling angles, there's actually not a direct relationship to which spin torque or driving moment you are utilizing. So actually, there's no direct relationship between the traveling angle, or the drive torque or the spin torque. Yeah. It's more related to the configuration of your CMG. For example, if you use adjacent pair, then there are certain axes that you must exert torque just through the spin torque. Yeah. But if you use the pyramid cluster, then you can fully utilize the gyroscopic moment, and then without sacrificing the power consumption. And for like this design here, this design only activates by one Single-Gimbal CMG. And actually, this type of CMG we call it the variable speed Single-Gimbal CMG. And then one axis needs to be provided by spin torque. Then you need to spin up and spin down the motor. So one axis is less efficient, the other axis is more efficient, because the spin torque axis is just as efficient as reaction wheel.
Absolutely.
Any more questions? If not, then thank you very much for your time today. And welcome to drop out our booths at Field House in 170. And also you are welcome to play this CMG in the front. Thank you.